Section 7.1, Exponential Functions, Growth and Decay. Essential question, please write this down. How can I write, graph, and evaluate exponential expressions? So who uses this? Collectors can use exponential functions to model the value of rare musical instruments. So there's this law called Moore's Law, and it's a rule used in the computer industries that states that the number of transistors per integrated circuit, which is the processing power, doubles every year. Beginning in the early days of integrated circuits, the growth in capacity may be approximated by this table. And when we talk about something doubling, we're using a certain function called an exponential function. And when we're dealing with an exponential function, we can see that the base, right here, b, is a constant, and the exponent, x, is the independent variable. B has to be greater than 0, and b can never equal 1. The graph of the parent function, f of x equals 2 to the x, is shown right here. Notice as the x values decrease, the graph of the function gets closer and closer to the x-axis. What's happening is it's getting closer and closer to a line called an asymptote. And that is a line that a graph approaches but never reaches and never crosses. And what's happening in this example is as the value of x gets very, 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 very large or very, very small, and in this example, as the x value gets very, very small, the graph approaches that asymptote. Now, what's happening when we're using this table of values, we have x values, and then the output obviously is the y value. You can pick any x value you want because x is the domain, and the domain in this case, like we mentioned, is right up here, is all real numbers. That's the domain. The range must be greater than 0. Y has to be greater than 0. All right, so in this example here, if I'm plugging in -2 into this function, I get 2 to the -2. Well, as we can see down below in this remember, when you have something raised to a negative exponent, you take the reciprocal of it to make the exponent positive. And that's how we got the 1/4. Plot the points, and you get the graph, which is an exponential function. So what we're going to find in this lesson is when b is greater than 1, that's called exponential growth. And when b is less than 1 but greater than 0, that's called exponential decay. Example 1. We're going to tell whether the function shows growth or decay, and then we're going to graph it. Well, in this case, b is equal to 3/4. That's less than 1, so that's definitely decay. We're going to find this information so that we can graph this. Well, a y-intercept, always x is equal to 0. So if I take my function and I set x equal to 0, anything raised to the 0 power is 1. There's my y-intercept. My asymptote is going to be y equals 0. It's that horizontal line on the x-axis. And then I can pick any two additional points. Well, the x values I'm going to pick is 1 and -1, just to make it easy to find a easy y value in this case. So if x is 1, we get 10 times 3/4 to the first power. Well, that is just going to be 7.5. And then -1, if I plug -1, I'm going to get 10 times 3/4 to the negative first power. Well, when something's raised to a negative, you take the reciprocal. So we get 4/3. And when we plug, that's like 10/1 times 4/3. When we plug that into a calculator, we get 13.3 repeating. So we'll just call that 13.3. All right, so let's graph that. Try that again. Okay. So x is 1. I'm going to, here, to make it easy, I'm going to count up by 5s. So over 1, and this is just going to be 1, -1. Over 1 up 7.5 is about right there. -1 up 13.3 is about right there. And we know that our asymptote is going to be this horizontal line. So when we finish the graph, it's going to look something like this. Exponential decay in this case, so the graph is going down and to the right. Exponential growth, the graph would be going up and to the right. Do example 2 in class. You can model growth or decay by a constant percent increase or decrease with the following formula. Little a is your initial amount. 1 plus r is called the growth factor. If it's 1 minus r, it's called the decay factor, raised to the exponential, or raised to a power of t, which is the number of time periods, and then we get our final amount. So let's do an example. Clara invests $5,000 in an account that pays 6.25% interest per year. After how many years will her investment be worth $10,000? Well, in this case, A is your initial amount, which is $5,000. R, well, that's 6.25%, but we must change it to a decimal. So that's 0.0625. If we forgot how to do that, there's a percent. To get a decimal, you move 2 places to the left. That's how I got 0.0625. So our exponential model then will be 5,000, 1 plus 0.0625, 1.0625 to the t. So that is the exponential function, and it is growth. B is greater than 1, so we're growing. When we invest money into an account, we're going to hopefully grow the money. So now we're going to use a calculator to graph it to predict when the value of the investment will reach $10,000. You're basically finding the t value where f of t is approximately 10,000. So how we're going to do that on our calculator is we're going to go to the calculator, graph y equals, we're going to plug in the function, and I'm going to demonstrate this. Then we're going to hit zoom fit to make the function fit on the graph so we can see it. Then we're going to hit second graph to get a table. And we're going to use the table to find how long it will take for the investment to reach $10,000. All right, so here's our calculator. And there we go. So 5,000. And I'm going to type in 1.0625 raised to a power and x instead of t, because that's what shows up on a calculator. Now we're going to hit zoom, which is up here, zoom. How you get to zoom fit is, if I'll show you, you just hit zoom 0, which is right there. And there's the graph. The graph is going up and to the right because it's growing. Now we're going to grab the table. Second graph. There's our table. And we're looking to see the first time the y value reaches $10,000, which is right here, which is after 12 years. That's how long it's going to take for your investment to go from 5,000 to approximately 10,000. So then I'm going to go back and we're going to write down some information, which we got from the calculator. From the table, we have our x, we have our y values, 10, 11, 12. When x was 10, the y value was 9168. X was 11, the y value was 9741, and 12 was 10349. And if we plugged in 12 right into here for t, which also we're calling x, into this function, we would get the 10,349. So to answer the question, how long will it take for the investment to reach 10,000? It's going to take about 12 years. We're going to save for example 4 for class, and there are video questions.